Yes, sir.
Okay, so the query is like this. I mean, I have given an example first. Let me explain it. I hope the yellow part, suppose if you concentrate on the yellow part here, this is program 1 and this is program 2. So I hope it is, yes. Any question? Okay. I hope this program is very easy to understand what it is doing, right? I mean, it is nothing but finding max between two numbers, right? So I can write this program in this way, which takes x and y to integers as input and just compare it and find max. I can write it in this way as well, where I default park it to y and getting x, I compare with y and then find max. So I can have several different implementation of the program. However, our logic helps us to formulate the guarantee where our precondition is true and check this post condition that if x greater than y and max equal to x or max equal to y is our post condition. And as you know that I want to guarantee that for every valuation of x and y, I can compute a max such that the precondition and the program execution gives me the post condition. And that is what the program correctness is all about. Now, how we navigate the program is through symbolically through all the paths. By symbolically means x and y can take any value of integers. So we assume x takes alpha, y takes beta, and then proceed. That is what the symbolical mean. That means any value alpha and any value beta, it should hold to satisfy the post condition. So with this example, let us try to understand what the query says. The first query is that if you look at the post condition, why not there is an implication between them, but I have given an and. Okay. So what do you feel? Why this is not an implication?
Sir, because that is not an assignment.
No, in deeper sense, if you see that what is this post condition is used for? It is used to verify the program, right? Given a precondition and through all execution paths, you are satisfying the post condition or not, right? So suppose I write a program where I just mistakenly make this x. I just mistakenly make this x. Then if you write such kind of a post condition, your post condition is satisfied, isn't it? Even if x less than equal to y, your post condition is satisfied. Yes or no?
Yes, sir.
Yes, sir.
But here, if you look at this one, your post condition fails because in this condition, with together max equal to x, this whole clause is false, right? And also this max is not equal to y, so therefore the whole post condition fails. So since we use it to verify programs, therefore we need to encode its internal conditions along with the outcome together. It's not the case if a condition holds, then this outcome. Because if this condition doesn't hold, you as a program writer may write a mistake to have the same outcome going in other branch, which if you write in this way the post condition, which will be eventually satisfied, which is not intended to be satisfied. So this is actually, we intent wise, the way we perceive this to verify is not being verified. So this is actually wrong. Clear?
Yes, sir.
Same, I mean, if you understood this, same is wrong if you try to write this kind of a thing, max equal to x or max equal to y. This also doesn't have the full intent of your program as a post condition. Because I can arbitrarily, as you do nothing inside the program, just assign max equal to x, then your post condition is satisfied, right? And same is the case if you write x greater than y, implies max equal to x, or x less than equal to y implies max equal to y. Because you know that if this is the case, it automatically is equivalent to the first one, right? This is equivalent to the first one. So all of these I put in red are actually wrong, considering the intent that I need to take. Clear, everybody who raised the question? Do you have any further questions on this point?
Sir, sir, in the second red statement, what if we replace the implication by double implication?
What if you replace the implication by double implication? So
Yes.
yeah, so see, if this, you just try to see the logical thing, you just try to do now. What is the problem? You are
Means
you are
if we
doing
write
this.
that ways, then it can be correctly represented. That is what I am trying to.
No, I'm saying that if this is the case, if this is, you are trying to write it this way, right? If this is the case, isn't it?
Yes, sir.
Then effectively you are telling A and B and not A and not B from the first part. From the first part, right? Yes or no?
Yes, sir.
From the second part, you are telling not A and and C. Or sorry, sir, I just have a mistake here. This is, yeah, this is, sorry, this is, sorry, this is A implies B and B implies A. So not A or B and not B or A. This is A or C and not C or not A. Right?
Yes, sir.
Yeah. So now try to see the intent that if you do if and only if, so you claim that this is the same intent that I want to say, that if and only if this happens, then this is. Then the only problem of this statement is that you restrict it with respect to this implementation. This implementation, where I do not have any else branch, this part where I do not have any else branch, this part that you make if and only if, this part is automatically going through. See, what does your if and only if statement here and here induces? It induces that this condition and if and only if this assignment, the condition negation if and only if this assignment. So this post condition inherently assumes in your program there will be an else branch as well. However, your program may be written in this way.
Okay.
Okay.
Yes, yes.
Yeah, just it's a logical juggler. It's nothing so difficult to think. But the question is that the whole purpose of this kind of post condition is to make sure that you verify the program along all the paths. So it should not be vacuously satisfied by some of the writings. So that's why you take care of every combinations of them.
Sir,
Yeah.
sir, the statement that you have written in the pink pen,
Mhm.
sir, what will happen if x is greater than y and max equal to y?
Max equal if x is greater than y and max equal to y, this will pass. This will pass. Therefore, the correct one is if you try to write here x less than equal to y and this. This is absolutely correct. Okay.
Okay. Okay, sir.
Sir, now
But I mean,
if we don't write x, if we don't write x less than or equal to y, sir, then is the post condition right?
no, because your friend has pointed out that if I make a mistake that
Yes,
if
in a
x
faulty
less than
program.
y, yeah, if I make a mistake of this, I mean, if I wrote the maximum program like this, if x less than equal to y, max equal to x, if I made this mistake. Or the other way, right? I mean, max equal to y was there, the other way. If x greater than y, I made this mistake that max is y. Then what will happen is the fact that this will satisfy now if I do not write the previous part. Right? Agreed, understood. But the problem is if I do not write the part that I added
Yes,
here now. So for the better representation, it is better to write it this way so that you can catch every possibility. The second question is, I think something is not articulated well. It's what is symbolic execution? It is nothing but executing through all the paths with a symbolic variable value to it. So if I have a program like if x is greater than y, x equal to y plus 1, y equal to y into 2. So what does the symbolic execution do? Symbolic execution will assign a value of x to alpha, assign a value of y to beta. After this statement, the new value of x will be beta plus 1. After this statement, the new value of y will be 2 beta. So after this statement, the next value of alpha dash will be beta plus 1. The next value of beta, that is beta dash, will be 2 beta. That's what this statement will do. And this progression is called symbolic execution. That's why in this particular case, we have true and alpha greater than beta. That means I am passing through the if path. Okay. Clear what is meant by this statement in true and alpha greater than beta is?
Sir, how are the two red statements equivalent? I mean,
Which one?
the two red statements, max equal to x or max
Oh,
equal to
this is logical jugglery, na? This is A implies B or not A implies C. That means B or C, na?
yes.
A implies B. What does it mean? It means not A or B. Not A implies C. What does it mean? It means A or C. So if these two combines with resolution, if we resolve these two, it is B or C, right?
Yes, sir.
So that is B and that is C. Okay.
Okay.
So that was some of the queries that you have raised in the logic.
Sir,
Yeah.
but these two should combine with the AND
Which
in
one?
the resolution part.
These two combination is obviously an AND. Combining means AND.
Yeah, sir,
When
but
we
in
write,
the written statement it is OR. Red one.
which one?
Sir, red one.
Okay. Yeah. I want to mean by this. Okay, I want to mean by this one. I mean, I try to say that if you want to replace it with implication, you do that both all possibilities, and all of them could has to satisfy, which essentially means either x or y, which is actually not correctly expressing the intent that if you go through if path and if you go through else path, you are not allowing the possibility of going through if path with the assignment. You are allowing the possibility that if you go through the if path, then the assignment goes. But in program, actually going through the if path may also fail due to your error, human error. Okay, but you are correct here. This is AND. Obviously, this is AND between two.
So for the second red statement, if x is less than y and max equal to x, then that will give false, right?
For the second statement, if x is less than y and max equal to x, yeah, that will give false because see in this statement it x less than y max equal to x, so this is false,
Yes,
right?
sir.
If this is false, then the whole thing is false.
But the above one will be true.
Yes, the above one will be true.
But then these two are not logically equivalent.
No. The see, you are saying see, you are saying this is true, but this is false because max, you are assigning max to x, right?
Yes, sir.
Now, if you are assigning max to x, then this statement is true. Your max is being assigned to x.
Yes, sir, that will be true. So the whole statement will be true, but the second red statement is false.
No, but what do you just now tell it? X greater than y, right?
Yes, sir. X.
Yeah. So see, I mean, anyone has to be
Less than y.
No,
X
no,
less
wait. This there is one mistake you are making. See, either this should be true or this should be true. Agreed? Since these are just opposite conditions.
Yes, sir.
So, for example, this is true and this is false. Right?
Yes, sir.
If this is false, then the whole statement will be true.
Yes, sir.
If this is true, and you need to make this part false, then your this should be false.
Yes, sir.
But max can take either x or y.
Yes, sir.
So therefore, if to make this to be false, you had to make max to y.
Yes, sir.
So if you had to make max to y, in that case, it will happen that the fact that see you are not making max to x and but max to y. So that means you are having a problem in your program. So this condition states that.
Sir, I didn't get the last.
No, I am saying that see, actually in our program, what is happening, let me take a fresh copy and tell you. Actually, in our program, our condition is I have x implies y and not of x implies not of y, because max can take only the value x or y. So if max doesn't take the value x, then max will take the value y. Right?
Yes.
So therefore, the post condition that you are writing is basically this condition is flipping here. Either max is taking x value or max is taking y value. So that means this part of the condition is also your negation. Right? Yes or no? Yes or no? Not agreeing? Okay. Let me write the big thing, then you will agree. First of all, tell me, if this is a condition x greater than equal to y and x less than equal to y, I call this condition A, I can call this condition not A. Agreed?
Yes, sir.
Okay. Now let's say max can take two values, which is x and y. Now, therefore, max equal to x, if this I call B, then max equal to y, I have to call not B. Agreed? Now, what was my post condition with respect to this? If x greater than equal to y, or let's say, let us remove equal to from here, let's put it here. If x greater than equal to y, I have max equal to x. So A implies B was our post condition, and not A implies not B. This was our post condition. Agreed?
Yes, sir.
If you simplify this, what it will come? It will come as B or not B. Right? Yes or no?
Yes, sir.
Now, you see what is my B? Well, my B is actually max is equal to X, and not B is actually max is equal to Y. Essentially, why you are finding these two are equivalent, because this evaluates to true and this also will evaluate to true considering the domain of max is X and Y. So your claim that you are making, that if I try to make it false, but make this one true, or rather the other way, if I try to make this as false, if I try to make this as false and still I make x as true, right? This is your proposition, that if I have this condition, x less than equal to y, max is assigned to x.
Yes, sir.
Then you are saying what will happen, since this is false, not a is true, and I assign max to x. So this becomes true, max to x means max equal to y false, and this is false, this is true. So you are saying this whole expression evaluates to false.
Yes, sir. But the second one becomes.
Yeah, but you are not considering that x and y are just the flipping of each other. X and y are just the flipping of each other. So essentially, that's why I made this step. Essentially, both are actually, this is kind of a nothing statement. See, if your max can take x or y value, if you give you the post condition that max can take x and y value, it is nothing at all, right?
Yes, sir.
So essentially, what you are feeling here, that these two may give rise to different result, is due to the fact that you are not considering x and y are the only domain of values that max can take. And if you consider that, so then both of the equation is actually a tautology in the post condition. You are giving nothing.
Sir, but we just got a condition where it's not a tautology, right, sir?
Why? B and not B is a tautology. This is also a tautology.
That is okay, sir. I mean the upper one, A implies B and not A implies not B. That is not a tautology, right, sir?
No, this is a tautology. I just derived it as a tautology. A implies B and not A implies not B is a tautology. Similarly, max equal to X or max equal to Y is actually a tautology in your program sense.
Sir, if A is
because max,
true and B is false, then we get it as a false. So it cannot be tautology, no, sir.
just come again.
A is true, taken as true, and B is taken as false.
No, just do this way. A implies B and not A implies not B. So this equivalence to not A or B and A or not B, right? Oh, wait a minute. This condition is OR. Wait. Okay, here is your confusion. This is OR actually. Boss, this you are wrong. This is OR.
Sir, actually, if that was AND, then it was the same as the post condition only.
If this was AND, this is the same as the post condition because A and A cancels. But this is actually OR, because see, if you have this one or if you have this one.
Sir,
this
then
should not be AND, because these two cannot be together satisfied.
Sir, then what about resolution?
Yeah, no, so now see now what will happen here. This is a tautology, and now this is also a tautology.
Yes, sir. If it is true, then it will work.
Yeah,
but
the thing is that resolution says in a different way. Resolution says it this way. Sorry, this is C. Then resolution says B or C. So F1 and F2 implies this. This is AND in resolution. So if I mean, we do not apply resolution to make these two equivalent. We just apply that the domain is the same, and therefore this both results in a tautology, and therefore the post condition is nothing.
Sir. Sir, A implies B or not A implies not B. The above yellow statement. I am not getting it equivalent to B union to not B.
No. This is not equivalent to this one. No, this is I just derived it this way. Now this is here.
Oh, okay.
Earlier this was AND. That's where I derived it.
Okay.
So again, I mean, to refresh what we have done. See, our condition was x greater than y implies max is equal to x, or x less than equal to y implies max equal to y. So what this results is actually, as this whole thing results, that max could be either x or y, anything, because that max could be x or y is basically you are saying nothing about it. It's a true statement anyway, because max can only take these two points. That is the main reason that this is not a good proposition, good post condition, because you are saying nothing about the statement.
Sir, if it is taken as AND, then that should be right, sir.
Yes, if you take this as AND, because
not that one, sir. This middle OR operator, if we change it to AND.
No. Then what will happen if you take it as AND? If you take it as AND, then this will happen, and not A or B, and A or not B. Then how does it simplify? It simplifies as A and B, or not A and not B. Right? Right? Yes or no? This I just broke it over this AND.
Yes, sir.
A and B, and then this is again with this one. There are 4 combinations. Not A and A is false, or B and A, or not A and not B, or B and not B. So there are only 2 remaining. So, but if you now say what is actually this is basically x greater than y. My B is actually max equal to x, and this one is x less than equal to y. My B is x equal to y. Now, this if you make, then this is the same as this pre-post condition. Okay.
Yes, sir.
And sir, if we put implication and AND in between them, then it will be the correct formula for the problem. Can we say that?
Just clarify again. X greater than y and max equal to x. This, or x less than equal to y and max equal to y is a correct post condition. Same we have found to be equivalent to x greater than y implies max equal to x, and x less than equal to y implies max equal to y. This is also correct because these two are equivalent, right?
Yes.
Yeah. What is wrong? Let me draw it. What is wrong? What is wrong is x greater than y imply max equal to x, so this is, or x less than equal to y implies max equal to y. What does it, why this is wrong? Because this or statement simplifies everything to be a tautology. Or in other sense, it also simplifies that max can take x value or max can also take y. Okay, so actually this simplifies it to this. In our context, it's a tautology, but if you also think that people can write an arbitrary max and assign it in your program, suppose I write this one, just x equal to 10, whatever be my x and y value, I do not care, I output max as 10. So your program is wrong, right? Your program is wrong, yes or no? If you just assign a constant in your program is wrong because you are not making the greater value coming here. So therefore, you see, if you write any of these post conditions, it will say x or y something. Any of these post condition, you see, this is not capturing properly the intent of the post condition. Suppose you just make it x, it will always output x. So then either this is true or this is true, because I have a or in between. So this eventually post condition will be true. If it always makes it yes, then this is true. So eventually this is true. Okay, so these parts are wrong. Wrong post conditions. Clear? Still doubt? Anyone has still doubt? I know. Am I audible, na, Professor?
Yes.
Yes, sir.
If you do you have still any doubt?
No, sir.
Okay. There is still a question that true and a greater than b is true, then the program executes. Yes, I already mentioned it here in the first slide. So this is a symbolic execution. This is a symbolic execution of the program. Suppose you write in a if statement x greater than y and do something. So in symbolic execution, you take the value of this to be alpha, take the value of this to be beta. When you symbolically execute, you make alpha greater than beta. And your precondition is true, and then your if branch proceeds. And if your precondition is true and alpha less than equal to beta, then your other branch, that is the else branch, or skipping the if branch, the rest part that proceeds. Clear?
Yes, sir.
Okay, so that's all. If you do not have any more query, then I will hand over to Professor Eddy so that he would make the other queries here.
Sir. Excuse me, sir.
Yeah.
Sir, in the array and indexing, that you explained.
Yes. Oh,
Sir,
should I?
Sir.
What is your question there?
Sir, in that you mentioned that there exists P and also there exists AP. Is there any necessity to mention there exists AP also?
Yes, because P is a different variable and AP is a different variable.
But P is referring to AP only, right?
Yeah, referring is a different thing. See, in your program, do you consider your index as a different variable and your location of the array are different variable? Yes or no?
Yes, sir.
So that's why here also in logic you need to consider these two as different entities. Okay.
But what are we logically saying here? Like there exists P and there exists AP in the same state.
Yeah, because logically we are saying we can find an index such that we can find a value in that index which suits to make our output true. There exists an index in the array is the first P. There exists the value in that index of the array is the second AP case, which makes your output happen. That's what we are telling here.
Okay, sir.
Okay, should I open up that particular part again for you? Just let me. Can you see this?
Yes, sir.
Yeah, here it is saying, see, for all valuations of the array possible and all indexes, that is the generalization of the array. I can find an index P and I can find from a value in that index P such that this works. Since this could be volatile, the P could be a volatile quantity, so there exists a P and the value at P location is also a volatile quantity, so there exists some value where I can make this true. Therefore, I take these two as separate. Clear?
Yes, sir.
Okay. Okay, I think I can switch over to Professor AD.
Hello, am I audible?
Yes, sir.
Okay.
Yes, sir.
So let us then come to the next topic, proof techniques. First of all, let me answer a couple of queries that I have got. So I should share my screen. Okay, so is it visible?
Yes, yes.
Okay. Okay, so these are small queries. So let me quickly address this. So query 1. So let us say A is a non-empty subset of B, and that automatically implies B is also non-empty. So I pose this question a little differently. So A is well ordered, implies B is well ordered. This is one assertion. Second assertion is B is well ordered, implies A is well ordered. Which one is correct? Which one is wrong, or both are correct, both are wrong? What do you think?
Second is correct.
Second one is correct. Why? Because if B is well ordered, then every non-empty subset of B has a minimum element, right?
Yes, sir.
But every non-empty subset of A is also a non-empty subset of B. Therefore, every non-empty subset of A also has a minimum element. Yes or no? So this is correct. Now what about this other one?
Sir, false.
False. Why?
Sir, we can take A is the set of natural numbers and B is the set of reals, which is a counterexample.
So this is false, for example, because of the fact that I can take A as the set of natural numbers, which is well ordered, and I can take B equal to real numbers. Okay. Okay, and the contraposition of this is, if B is not well ordered, then A is not well ordered. So this is false. If A is not well ordered, then B is not well ordered. This is true. Right. So the contrapositions, if I write,
A is n plus, I guess. A should be for the false case.
A is
A equals to n plus.
n plus means
N greater.
no, n is the set
sorry,
of
sir,
positive.
I got confused with integers. Sorry, sir.
Yeah, it's, integers are called z. Okay, this is natural numbers. So the contraposition. So A is not well ordered, implies B is not well ordered. This is true, whereas this contraposition, B is not well ordered, implies A is not well ordered. This is false. So is this query answered?
Yes, sir.
Okay. And there was second query. This is just maybe a matter of misunderstanding. So I told, let's say that alpha is an integer of the form p1, p1, p2, p2, pk, pk. Then I claim that alpha square has 2e1 plus 2e2, 2ek prime divisors. Okay, the query was why. I can see that only there are k prime divisors. Of course, here I am counting the prime divisors with multiplicity. Okay. So alpha square has k distinct prime divisors. That is true. But in the proof, I was not considering distinct, the total number of prime divisors, counting the multiplicity of each prime divisor. So that was the confusion. Is it clear? Yes or no? Anyway, I do not see any response. This is fine, right?
Yes, sir.
Oh. Okay, so these are two small queries. Let us now solve some exercises on proof techniques. I will try to give you a wide spectrum of types of proofs. So let us start with this. Okay, just read it. The game of NIM is played by two players, A and B. There are two piles with M and N sticks. The moves alternate between Alice and Bob. And Alice starts. Okay, so what I forgot to mention here, Alice starts. Alice makes the first move.
Sir, it is written already.
Is it written somewhere? Oh, okay. It's there somewhere. Okay, fine. Anyway. Yeah. So the player who fails to make the next move, that is the player who makes the last move, wins. Okay. And the player who fails to make the next move loses. Alice makes the first move. Then, what does these assertions say? The first assertion says that if M is equal to N, that is both the piles have the same number of sticks, then if Bob plays optimally, I mean intelligently, then he can always win. Whereas if M is not equal to N, Alice, if she plays intelligently or optimally, can always win. In other words, if M is equal to N and Bob is optimal, then no matter whatever Alice does, she cannot win. Whereas if M is not equal to N and Alice is intelligent, plays optimally, then no matter whatever Bob does, he cannot win. So how to prove such a pair of statements?
Sir, in part A, can we proceed by induction?
Like, you tell how?
Let us say M is 1. So Alice will pick at least one stick, and can pick only one stick means from one of the piles, and then Bob will pick. Then Bob will surely win if m is 1. Now, for higher values of n, like let us say at particular instance, we start from m sticks in both the piles, and in the first move, Alice picks k sticks from one of the piles. Then what Bob can do is that Bob can pick k sticks from the other pile, so that at each after two moves means one move of each, we always have a situation like m minus k sticks in both of them. So
Yes.
eventually we will reach to 1 comma 1. So and Alice will have a move. So Bob will always win if m is n.
Of course, you can stop at 1 comma 1, but better thing is the losing condition is 0 comma 0, not 1 comma 1.
Means one or more sticks are to be removed then.
Yeah, so when the player fails to make a move, that means both the piles are empty. 1 comma is not the end game, because the game will still continue. Yes or no?
Yes.
Okay. Okay, so essentially it's a kind of inductive proof. So part A, the essential thing that Bob can do, Bob simply imitates Alice. So M, so Alice takes K, then what Bob will do, Bob will take K sticks from the other pile, so that this condition M equal to N is always satisfied. And if this thing continues, eventually it will be 0, 0, and then Alice will face the turn. And loses, because both the piles are empty. Yes or no?
Yes, sir.
Okay, so this is a kind of inductive proof. But what about B?
So the same thing. The Alice can pick the number of sticks from the high pile, which is higher number of sticks, and make it equal.
Oh.
Then it will become the same game where Bob starts. So she will win.
So Alice forces M equal to N in her first move. Okay. And then the situation just gets reversed. Okay, so anyway, this is a simple exercise. Let us do something a little bit, I would say, number theoretically useful. Let A and B be two positive integers having GCD D. Then you have seen that I can find two integers U and V such that D can be written as a linear combination UA plus VB. Okay. Now, what I want to demonstrate is that I can always choose U and V. Of course, this U and this V are not unique, but I can choose U and V such that the absolute value of U is no bigger than or strictly smaller than B by D, whereas the absolute value of V is less than equal to A by D. And except for, I would say, very esoteric conditions, this is also less than. Anyway, let's not worry too much about this less than or less than equal to. So how we can prove? Obviously, induction does not seem like a good idea here.
Hello, sir.
Yeah, tell.
Sir, I have a doubt actually. Sir, if we take b is equals to a, then GCD of a comma a is equals to a. So I can take u is equals to 1 and v is equal to 0. So the first condition seems to be like not valid because 1 is less than 1.
No, you do not understand you do not write it. Read it. I can choose u and v.
Oh, okay.
Okay, I can take u equal to 0, v equal to 1.
So this means that we have to prove that there exists at least one solution that satisfies this.
Yes.
Okay.
A equal to 10, B equal to 15, U is minus 1, B is 1. Then what do you want to say? Have to prove for all A and B. Yeah. Okay, maybe it's a little bit difficult to start with, so I will give you an
So if you
initial.
take B equals
Uh-huh.
A by D,
U
then
by
you can
D.
derive a value U which will have modified.
What?
If B equals to A by D, then we can derive it in that condition. V equals to A by D.
Okay.
And then we can derive a value of u which will have modulus less than b by d.
Okay. So here is the suggestion anyway.
Sir,
Yeah. Then.
we can write A as K1D and B as K2D, where K1 and K2 are positive integers.
Okay.
Then I can write D is equal to UK1D plus VK2D. And I
Yes.
can cancel D from both sides.
Yeah,
Then
yeah.
I have
That's precisely what I am trying to tell. Let us say alpha equal to A by D, beta equal to B by D. Then if I substitute this and cancel D, this becomes much simpler. U alpha plus V beta. And I have to show that I can choose U less than beta and V less than equal to alpha. And this looks like much, I would say, simpler. Yes, that was a good first step. Then?
Sir, then we can write U greater than minus beta less than beta. And V less than alpha less than equal to alpha and greater than equal to minus alpha. Now alpha and beta are positive, so that we can multiply inequality on all the three sides and add the two inequalities. Then we will get U alpha plus V beta less than alpha square plus beta square and greater than minus alpha square minus beta square. And since this is a positive sum of squares of two positive integers is always greater than equal to 2. So 1 will always lie in this range.
No, I do not understand your query, but your solution. Yeah, it's true that if I put all values of U and V, so that U is between minus beta and plus beta, V is between minus alpha and plus alpha, we can perhaps bound this quantity U alpha plus V beta to some negative thing to some positive thing. Question is, why is 1 achievable in that range? Yes or no? Okay, I will get a set of values bounded below by something, bounded from above by something. Why should 1 be there?
Sir?
Yeah.
A by D and B by D will be co-prime, sir.
A by D and B by D are co-primes, yes.
So there's a theorem which says that so the GCD of A by D and B by D will be 1.
Yes.
And so we know that the lowest positive value that U into A plus V into B can take will be the GCD of A and so over here you get 1.
That's what it's written here, right? 1 equal to U alpha plus V beta.
Right. So but like that, I can propose a different proof. So we know that D is equal to UA plus VB. So we can find U and V such that you get this. Now we'll substitute U as U minus B by D and substitute V as V minus A by D. So doing so, you'll still get the value of the expression to be D. So you can keep doing that for as long as U and V are positive integers. You'll find we get a solution.
That's a positive direction. So I have to U alpha plus V beta. So I can anyway take any Q, subtract beta, V plus Q alpha beta. So minus Q beta alpha plus Q alpha beta. So these two things cancel and I still have this original equation. Yes or no? Or if you just keep on having this A by D, B by D here multiply this fixed by d. You can do that, but anyway, this becomes slightly more, I would say, easier to deal with symbolically. Is this fine or not? Okay.
Yes, sir.
Okay, so what I now do, I divide u by beta. This is Euclidean division. Divide u by beta, write it as q beta plus r. Then I have 0 less than equal to r less than beta. Because this is the remainder. Yes or no?
Yes,
sir.
Okay. So then for this particular choice of q, I have r alpha plus s beta, where this q corresponds to this. Okay. So I already have 0 less than equal to r less than beta. This quantity is satisfied. This inequality is satisfied, right? Yes or no?
Yes, sir.
Okay. So now I have to show that S is less than alpha. For this particular choice of Q. Okay. So this is now not that difficult. R can be 0. If R is 0, then I have S beta equal to 1. S is 1 over beta. Therefore, this is less than equal to 1, which is less than equal to alpha. Beta is an integer, right? So 1 by beta cannot be bigger than 1, so less than equal to 1, and this thing. And if R is positive, then what do I have? Maybe I just... Will you work it out? It's fairly straightforward. If R is positive, then what is S beta? 1 minus R alpha. Okay. And R is an integer, alpha is an integer. Okay. R is a positive integer, alpha is a positive integer. So the absolute value of S is actually negative, will be R alpha minus 1 by beta. Yes or no?
Yes, sir.
Okay. Then what do I do? This is certainly less than R alpha by beta. And here you see R by beta is less than 1, so this is less than alpha. Yes or no? Happy?
Yes, sir.
Okay. Okay, incidentally, this is actually, tell.
Sir, R alpha plus S beta is 1, but we have one more condition that R and S both must be integers. So for R is equal to 0, if we means, how is it happening? I did not understand that step.
R is 0, so S beta equal to 1. Actually,
means S must be an integer as well, right?
Actually, that will force S equal to 1. Beta equal to 1, S equal to 1. There are no other possibilities. Okay, so actually this part you can S and beta are integers, so it actually implies S equal to beta equal to 1. And therefore 1 is less than equal to alpha. Now you can also use this reasoning. Yeah, that's also fine. Yeah, it's fine.
Okay, sir.
Yeah, that's true. Actually, this is a bad case. In general, we have this. Anyway, let's not worry too much. Yeah, that's true. You are correct. Yes. Yeah, any other queries? Okay, maybe then let us switch to another exercise.
So in that previous sum.
What?
So can we use these conditions which we have to prove and prove that like there exists one in the range of u alpha plus v beta? Like can we go in that way?
I do not understand your query. So you choose u and v in that range, right?
Yes, yes, sir.
And then prove that one will appear somewhere there.
Yes, sir.
That was your proof idea, right?
Yes, sir.
Yeah, if you can do it, it's fine. Maybe using pigeonhole principle or something like that, you may be able to prove it. I am not very sure, but it is possible perhaps. Yeah, I think it is possible that way.
Also, sir, we shall also prove u less than beta, right?
No, I don't understand your query. Yeah. So let u vary from minus beta minus 1 to plus beta minus 1. And v let it vary from minus alpha to plus alpha, and then you count how many things are there and what is the maximum possible value for this, minimum possible value of this, and then somehow prove that there must be a repetition and do some kind of jugglery. Yeah, by pigeonhole principle, perhaps you can prove it.
Sir, here we only proved s less than alpha, but we don't know whether s is greater than v or less than v. So, did we prove that v less than a by d?
Alpha is right?
Yes, sir. But we proved that s is less than alpha, not v is less than alpha. Here
Not?
s is v plus q alpha, and that.
Okay. Now look at this. This is now my new u. This is now my new v. Okay. So just think of this as my new u. Think of this as new v. Okay. So instead of r and s, I could have written u prime v prime. Okay. So I can start with any u and v, but eventually I get some u and v after these operations which satisfy this. Okay, so if I call it u prime is less than beta. If I call it v prime is less than alpha. Okay. Yeah.
Sir, one more doubt.
Yeah.
We are writing s beta as 1 minus r alpha. So 1 minus r alpha is an integer, but how are we sure that it will be divisible by beta? Because s is integer, beta is integer, but means 1 minus r alpha is always composite. How are we arriving at that result?
This is guaranteed by this equation, right? Because 1 is equal to r alpha plus s beta. This is true. There exist integers r and s, alpha and beta, such that 1 is equal to r alpha plus s beta. You do not have to prove that s is an integer. S is already an integer because it is of the form v plus q alpha.
So you can prove by taking v equals to alpha. Then we get q equals to 1 by alpha minus beta.
No, I don't understand. The way I have constructed r and s, they are integers, right? This is nothing but B plus Q alpha. B is an integer, Q is an integer, alpha is an integer. So S has to be an integer. I do not have to prove that it is an integer. Yes or no?
Yes, sir.
Okay. Okay. Any other queries? If not, just think over this. Maybe I will just take a small break, 5 minutes break. Meanwhile, you think about this. Maybe I have used a notation here, which is not yet introduced. So whenever I say some x divides y, this means y is a multiple of x. Okay, possibly I have introduced this, I will introduce this divisibility symbol in a later, I would say later class. So this means if BC is a multiple of L, then either B is a multiple of A or GCD of AC is greater than 1. Okay, so think about this. We will come back.
Eddie, just one point.
Yeah.
Can I clarify one doubt, because there is one resolution question. I also get it from some students' mail. So just when you go 2 minutes, I will take to clarify that.
Okay, so then I will just temporarily. Okay, so I hope you have remembered this question. If not, you just write it down. I will stop my.
Yeah.
This is fine, right? I will stop my presentation then. Okay.
Okay, just one question you had. I think that is a doubt that you have made. Can you see my screen properly? Can you all see my screen?
Yes, sir.
Yeah. So one of you have questioned me about the resolution thing. I say A implies B, and also I say A not A implies C. Then how can I claim this is to be B or C? Because in resolution we claim that this is not A or B, and this is A or C. And in resolution we come down here assuming this is an AND, right? Because you have given a counter example showing me that if, let's say, this is true, this is false, obviously this is false, and I can make this as anything like true. So therefore F and true, this results as true. However, you see, since this is an AND, so true implies false, outcome was true. Sorry, outcome was false, ANDed by true, which results you false. Right? This was some question. Do you get the question that where is the fallacy I am asking for?
But sir, everything above the line is assumed to be true, right?
Yes.
Above
So actually resolution refutation doesn't make equivalence between these two ANDs and this one. Resolution refutation means if F1 and F2 gives rise to a goal, it means F1 and F2 implies G is a tautology. Okay. It is not the case that F1 and F2 is equivalent to G. This is not the case. Okay, clear everybody?
Yes, sir.
So this means this one. This does not mean this one. Okay, this does not mean if and only. This means only one sided. This is a tautology. Okay.
Sir, we can also write F1 and F2 and G implies total, right?
No, you can write F1 and F2 and not G is a falsification because negation of the whole. Okay, this is same as this. Clear?
Yes, sir.
That's why you are saying that I put max equal to X here to be false and then make this part as false, but how my this part is getting true? That is not the resolution principle. Resolution principle is assuming this part to be true, you will get this part also. Not making the
Excuse me,
previous
sir.
part false. Yes.
Sir, am I audible?
Yes, yes, yes.
So why you are making B as false?
No. I am trying to show you that there could be assignments where F1 and F2 may be false, where F1 and F2 may be false. Yet this could be true.
Okay, sir.
But this does not refute the refutation principle logic, which actually says if your premises are assumed to be true, your goal is true. So which actually says that this and this imply B or C. The whole thing is a tautology. Okay.
Sir, can't we say that F1 and F2 and G is a tautology?
No, never. You cannot say that. You cannot say that. F1, F2 and G is a more stronger condition than this one. Because you can say this way, F1 and F2 and G or not F1 or not F2. You can say this. This is a tautology. Because only this one is very stronger. Na? You have to make these two both as true. Whereas this is also true when any of them is false. Agreed?
But sir, in resolution, we assume that F1 and F2 both to be true and we prove that G to be true.
No, resolution principle says that if F1 and F2 are true, then you can just eliminate F1 and F2 and add G as an equivalent to that. Assuming that is to be true, not assuming that is to be false. Still doubt?
No, sir, fine.
Oh, good. I am just stopping the sharing because Professor Eddy will resume.
Okay, Professor H, are you done?
Yes, I'm done.
Okay. So let me continue. I am back. Yeah. Okay, maybe just before solving this, I need to, in fact, we all both need to announce that next Tuesday in the regular class time, we are going to have our first test. Okay. So, I do not think we have enough time today to solve several exercises, at least a few exercises on induction. And induction will be part of your syllabus. So shall we have a meeting on Monday? Tutorial session on Monday? It is 12 to 1 or 11 to 12, something like that.
12 to 1. Monday 12 to 1 we can take with some other problems.
Because I do not think I will be able to cover too many exercises on induction, which is a part of your test 1 syllabus. So let us have a tutorial session next week on Monday. Fine, right?
Yes, sir.
Okay. Okay, so now let us concentrate on this.
Sir, will the test First, include the syllabus covered till now,
Uh-huh.
or will the test includes the syllabus covered till now, or also in the from the upcoming videos?
Let us say induction is there, but whatever follows induction, like recursive constructions and okay. So maybe I just make it clear. Test 1, syllabus, up to induction. All forms of induction, weak form, strong form, special form, and all these things. And I think just the first video of this week that will cover the generalized induction forms. Okay, so if I am not mistaken, so includes video 1 of this week. So we need to see some applications, some sample exercises on this different types of induction. So let us have a meeting on Monday, next Monday. Okay, so let us now come back to this.
Sir?
Yeah, tell.
Sir, actually I had a small doubt in the before question again.
Question. This one.
Yes,
Yeah,
sir. Sir, in this we are considering there exists u comma v integers such that u alpha plus v beta equal to 1. And then we are manipulating them to find new integers r comma s which satisfy the conditions given in the question.
Exactly. Yes.
So, but then we do need to prove first that there exists u comma v integers such that.
No, this follows from this, right? Extended GCD, is it not part of your some of the videos? I think so. So this is this is the original thing, right? This D can always be written as a linear combination of A and B.
Yes, sir. Got it.
Okay. So this is already proved. Based
Yes,
upon we proceed. Yeah. So any I would say suggestions how to solve this?
Sir, we can rewrite this as A divides BC and not of GCD A comma C is greater than 1 implies A divides B.
Exactly. Good. So this is called a syllogism, a disjunctive syllogism or something like that. So I will assume A divides the product BC and GCD AC equal to 1. So to prove A divides B. This is a nice way of proceeding. Then?
Sir, now from the statement GCD of A comma C equals 1, we can say that there exists two integers u comma v such that UA plus VC equals 1.
This implies there exist integers u and v such that 1 is equal to UA plus VC. Then?
Sir, we can rewrite this as VC equals 1 minus UA.
We can rewrite it as?
VC equals 1 minus UA. Just.
Okay, yeah.
Sir, then we can write from the statement A divides BC that there exists an integer k such that KA equals BC.
exactly do not follow your argument. But anyway, I think let us, instead of writing that, just multiply this by b. Fine, right? Now I see that the right side, this is a multiple of A. Moreover, BC is a multiple of A. So this is a multiple of A. This is anyway, you can see that this is a multiple of A. So this is a multiple of A plus another multiple of A. So the total thing is a multiple of A, and that is what we wanted to prove. B is a multiple of A. Yes or no?
Yes, sir.
Okay.
Sir,
Yeah, tell.
sir, if BC divides A, then
No,
it
A
is
right.
automatically the case. Okay, sorry, sir. If A divides BC, then it is automatically the case that A divides B.
No. No. Why? So consider this A. A equal to 4, B equal to 6, C equal to 10. So 4 divides 60, but not 4 does not individually divide 6 or 10.
Okay, sir.
Okay.
So can we say that if A has suppose like prime factors, prime factorization has like K prime say P1, P2, so until Pk, and then since GCD of A and C is 1, that would mean that C, none of those prime factors divide C. So that means all of those prime.
That way also you can argue, using prime factorizations of A, B, and C. Yes, that's another proof. Yeah, that's also a very valid proof. Yeah, you can proceed like that. No problem. Yes or no? Okay. So I hope there are no more doubts here. Okay. For the moment, let us say that I will not solve this. You think about this. And since this is a starred exercise, this means it's difficult. But still doable with the I would say mathematics you already know. So just keep it in mind and try to solve it offline. Let us look a little bit on induction. So just note it down. And if you want, I can give you a hint at this moment itself. So do you need a hint? Yeah, tell something. Yes or no?
Sir, we would like to try this first. Sir, could you please give the hint in the next Monday?
Okay, okay. Okay then. Fine. Fine. Okay, now let us do something on induction. Maybe this is our first thing. This is just induction in 2 dimensions. Let S be a subset of N0 cross N0, that is a pair of all non-negative integers. It is given that 0, 0, it is in S, and also that whenever some m, n is in S, we have m plus 1, n is in S, and n, n plus 1 also in S. Then prove that S is the entire set n naught cross n naught. So you know this Cartesian product, right? Set of all pairs. Cartesian product you know, right?
Yes, sir.
Okay. Yeah. So what should be your first line of attack?
Basis.
Huh? What?
So base case.
No, I do not understand your
The
whatever.
base.
Can
Huh?
Yeah, first we will say base case then.
0, 0 is kind of base case, yeah.
Yes, first we will we'll prove linearly for 0, n and for m, zeros. Then from each linear we can, from that each linear we can, like from horizontal we can prove vertically then, and from vertical then we can prove horizontal from each point.
Okay. Okay, that is a way you can do it. Let me see if. Yeah, that also you can do. Yes. Yeah. Hey. Any
Sir,
other
can we
suggestion?
do an induction on minimum of m, n?
Let us see whether we can proceed like that. Proceed by induction on minimum of m, n. Can you proceed?
Sir, can we do that like for any m, n?
Yeah.
We have all the points to the right, which are like a, b, which is a greater than m and b greater than n. We have all the points to the right and top. So, and since 0, 0 is there, so then we have all the points a natural number and not and not.
Well, this is, I mean, a little bit of hand waving. The earlier, the first suggestion is fine. Prove that, okay.
So,
Sir,
Yeah, tell.
sir, suppose it is given that 0, 0 can be accessed. Hence, all points of the type alpha, alpha can be accessed.
Alpha, alpha is not a good thing. Okay, let me point out whatever you have mentioned. If I use 0, 0 in S and m, n in S implies m plus 1, n in S, then using those two things, if I take n equal to 0, I can show that this is induction, right? Induction only on the first coordinate. Yes or no?
Yes, sir.
Yes, sir.
Oh, good. So now fix any m. You have m, 0 in S. Also, you have the second thing, m, n in S implies m, n plus 1 is also in S. 0 is there. If n is there, n plus 1 is there. Then you prove that m, n in S for all n in n. Happy or not? But then I have fixed any m. M can be anything. So this is established for any m, n. Happy or not?
Can you repeat? So can we take that? Can we fix n instead of fixing n equal to 0 only?
No. Then you will prove it only for this number. This number 0, this, and this number, this pairs. But I want m, n to be anywhere.
Yes, sir. Why did you take n equal to 0? That's what.
Yeah.
Yes, sir.
Yeah. This is for beginning the induction on the second coordinate. Just I take n equal to 0. Just write 0 here, 0 here. This is by this thing. Then I proved that m, 0 is in S for all n. Okay. Then I fix an m, start with 0 here, and use this n to n plus 1, and prove that m, n is in S for all n in S. Okay. So that essentially means I have first proved this is there, this is there, this is there, this is there, this is there. All these things are there. This is the first thing I proved. And then starting from any point here, I will prove this is there, 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 and this is true for all. So this is the geometric insight in it. If I start from this, I prove this is there, this is there, this is there, this is there, and so on.
Sir, what if we start with by fixing any value of n instead of fixing value of n in other than 0?
Yeah. Fix any value of n other than 0.
Yes. If we start with that, even then we can prove it.
But where is it? Let's take n equal to 1. Okay. So 0, 1 is in S. This is not given, right? This is not part of the hypothesis.
Can you
yes.
repeat?
Right. So first we have to prove that that thing is there, 0, n is there. Okay, so either way you proceed, you have to do something like that. You first prove that this is there, this is there, this is there, this is there. And then you prove this is there, this is there, this is there, this is there, and so on, whatever.
Sir, I didn't get what shall we do to prove first?
No. If you start with n not equal to 0, you cannot proceed by induction because 0, n is not given to be in S. This is not part of the hypothesis. First, you have to prove it.
Okay. If we don't take that, then we shall start with m equal to 0.
Yeah, in that case, you have to start with m equal to 0. Yes. Yes. So another possibility you can think about this, you can use well ordering. This is another way of proving it. So you can proceed and see. 1154, maybe I will just introduce another simple exercise. Yeah. You read it and solve it. It's fairly straightforward. Reading will take some time, so you take your time to read it. Yeah.
Sir, I think the problem is with the base case. If the means we have to take base n is equal to 2, then this theorem will be correct. Right. N is equal to... Hello, sir. Hello.
Yeah, tell.
I think the base case is means low. It should be 2 for means to theorem to be true.
Is there a problem with n equals to 2?
There is a problem with n equal to 2. N equal to 1 is the base case, no problem, right? Why is the base wrong? If there is only one hertz, then it's of the same color.
Yes, means for the theorem to be correct, we need to take base equals to 2, and we have to prove first base equals to 2. Then the theorem will be correct. Otherwise, we cannot prove it.
No. If I take base n equal to 1,
yes, sir.
Is this a false statement? If there is only one hertz, it's of the same color.
Sir, I think the problem is with the any group of n minus 1 hertz.
So this statement, if you look at this statement, this is not a logical problem. This is obviously true. This is true. There is no problem here. So there is no point starting from n equal to 2.
Sir, but saying any group of n minus 1 is wrong, right?
No, what is the problem? You just try to identify.
Sir, in the last statement, it says that the ones that were not discarded. So that group is of size n minus 2, so we cannot induct in that way.
As the one that were not discarded. So here this is the problem. If n equal to 2, there is no such horse.
Sir,
Yeah.
sir, if we take n equal to 2, then the theorem says that the remaining n minus 1 horses are of same color. So from there we can conclude that both the horses group are of same color, but it does not states anywhere that both the horses are same color.
Yeah, so that's the problem. N equal to 2, so you have something like this. There are n horses. You say that this n minus 1, they have the same color. This n minus 1, they have the same color. And then you discard this and this. Then if you can find a common horse here, these are of the same color, these are of the same color, and therefore all the things have the same color. But if n is equal to 2, this region is empty. Yes or no?
Yes, sir.
Okay, and therefore for n equal to 2, this is not a valid inductive argument. Yes or no?
Yes, sir.
Okay, so that's the fallacy here. So all n must have the same color as the ones. Now, if there is no such horse, then this argument cannot hold. Right?
Yes.
Okay, but then this also suggests that if so if I force that this is 2 for n equal to 2, then there is no problem with this. Yes or no?
Yes, sir.
Okay, yeah. Anyway, so this is a kind of, I would say.
Sir?
Yeah.
Sir, if any two horses are of same color, sir, then how it implies that all horses are of same color?
Then this is.
I can select any two horses, the two specific horses from the group, and they have same color.
No, if
So how
any
it
horses. N is actually a little bit confusing. How do I write it?
All NC2 horses are of same color.
Yeah, this is what I meant. Any is anyway actually is, we should not use any in
Sir, or we can write that if no two horses are of different color.
yeah, that's better. Yeah, that's better. So any is a little bit confusing, or we can write all. Yeah, maybe I write it that way. If no two horses are of different colors, then all horses are of the same color. Yeah, that's true.
So what is the problem with any? If we say if we choose any set of two horses, then they will have same color. Then it will include all sets.
You understand? Yeah, let's see. So let's look at these two statements. Okay, I am free on any day, which means I am free on all days. Yes or no? And if I say something like this, if I get any free day, I can finish the job. Something. Finish the assignment or something. Here, this n is actually implying there exists. If there exists a free day, I can finish the job. Whereas if I like this, I am free on any day, this means I am free on all days. So this any is actually confusing. Yes or no?
Yes, sir.
Okay, but so it's preferable to avoid any in these mathematical statements. Sorry, it's my mistake. Okay, any may mean for there for all, or it may also mean there exists. Okay, it's confusing. Okay, so
but sir, here,
yeah.
Here in the two statements, in one statement it is for all, in other statement it is there exist.
Yeah, so any should be avoided in mathematical statements.
Yes, but I'm saying that in this case of horses, this any refers to for all. Can I say that?
I understand that with that intention I wrote it. It essentially means for all, but if somebody interprets it the other way, I should not blame. The blame is on me, not on the interpreter. Right? You try to avoid any. Try to avoid any in logical statements. It may mean both. Okay. Okay, so this still leaves us with some more involved exercises on induction. So I think we should stop here because it's past 12 already.
Yes.
Yeah, so let us meet again on
Monday.
And Professor Hajra, do you want to tell something about the logistics of the test?
Yeah, I just wrote it because we are, but just one point, it will be subjective and problem solving in nature pattern. Secondly, you have to write the answers in a piece of white paper and scan photocopy it so that it is clear to be readable by us. And make a single PDF, okay? Not multiple things you can upload. We will give only single position to upload one file. And make it less than 5-6 MBs. Not make it too huge, but readable. That is mostly important. Okay?
Sir, solutions included.
Solution?
Included.
Where included?
Solutions.
I could not understand your question.
Sir, are the solutions to be included? You just said about answers.
Yeah, I mean, we will give you a question paper, and accordingly, question number 1 you solve, question number 2 you solve, so that you solve in a piece of paper, and then if there are multiple paper, photocopy it, make a single PDF, upload the whole thing. I could not still understand your question.
So he is asking whether to write only the answer or with detailed solution.
No, you have to solve the problem means you have to write in such a way that at least we can understand your steps and how you proceed for the solution. It is not the case that a count is asked, just write the count as an answer.
Yeah, it's something like this. This kind of small arguments you have to. It's not like the answer is 15, answer is 31. You just write 31. It's not like that. This kind of argument you have to give. Okay.
That's why it's a subjective answer you have to give.
These are not multiple choice or numeric questions.
Okay, and Google form we will primarily do it. Either the question paper we will upload somewhere and link, or send it somehow. I mean, that leave it to us. But there will be only one position to upload one file. So please make sure at your home how you combine and make it a single PDF of reasonable size.
In the worst case, you cannot do it. You just combine all your JPEG files or whatever PNG files in a zip file and upload that.
Zip file and upload, yeah, in Word Space.
Prefer to create a single PDF.
Okay.
So can you increase the size, maximum size, so that it won't create last minute problems?
You photocopy, let's say 10 pages and then make a PDF in a compressed version. You tell me what is your size coming. It will not be more than 10 MB. I mean, we have done it in the last year.
Yeah, don't submit to huge files.
Yeah.
Yeah, maybe keep it to within 10 MB.
Within 10 MB. Keep it within. It will be within 10 MB. If you go ahead, you will find it. It will be within 10 MB.
And if needed, you just make some practice. And yeah, don't try it for the first time during the test.
Yes.
Okay, make some practice of how to make a single PDF out of let's say 5 to 10 pages and all that. Okay, don't keep this experiment for the last moment. Okay, then you may have problem. Okay, make a little bit of practice.
Okay, then I think we are done for today. I'm stopping the recording.
Sir, the videos of this week will also be included in the test, the syllabus.
What?
Sir, the video that you upload this week, will that also be included in the syllabus?
No, that's what I mentioned. I think the relevant thing will that completes this induction part is only the video 1 of today this week. So video 2 and 3, this material will not be covered. So I mentioned it somewhere, right? Yeah, includes video 1 of this week.
Okay.
All parts of induction, but not applications like invariance or recursive constructions. Okay.
And sir, means here is it like that we are not allowed to navigate, so we have to solve the first question and then only we can see the second one.
No, we will give you question paper.
Okay.
Sir, and the test is going to be for complete 2 hours during the class time.
No, shorter than that.
Around 1 hour you can.
Around 1 hour it will be.
So how many questions will be there?
Around 1 hour, how many you can solve, we will solve. Okay. So we will be meeting again on next Monday. Thank you.
Okay, so next Monday we'll solve maybe 4 or 5
questions
for serious exercises on induction. Okay, bye.
Thank you, sir.
Thank you, sir.